Today is our first formal class, June 1st, 2020. And the topics that we're going to cover today are very simply linked structures, okay, or objects. So there was a video that I previously shared with you, and I'm happy to say that most of you have already watched the video. So that's going to be a good starting point. But I'm going to go over the topic very closely because what we're going to study today is very important, and this is going to concern all of our material until almost the end of this semester. So let's start with what is linked structures. So yesterday we briefly talked about Java's classes, objects, how do they work together. Okay. So if you've already watched the video, there was one point which was very important, which is that how do we store information using any programming language? So let's go with Java. So we have two ways of storing information. We either create variables. Okay, so for example, integer x. So when you say integer x, what happens is in your environment, x works as a pointer, okay, that points to a memory location. So yesterday we tried to imagine that the RAM in your computer works like a very large single-dimension array. So whenever you declare something, whenever you say something like integer x, it's going to go and take a chunk of memory, and assign it to x. Now when you say x equals to 5, for example, okay, so your program knows that in your environment there is some memory location which is referred to by the variable x, and we simply go and put 5 in that memory location. As a programmer, we don't have to worry about these things, okay? Where exactly this memory, what part of RAM contains this particular chunk of memory, we're not really concerned about that. We assume that the Java Virtual Machine, JVM, is going to handle all of the addressing. Okay, so in the video that I shared with you earlier, I've gone into more detail about how addressing works. Today I'm not going to talk more about this, rather we're just going to focus on how objects work. Okay, so we have a few ways of creating things. I can do something like this. I can say integer x equals 5. Okay, I can also create an array. Let's say a equals to new integer 3. Okay, so what happens over here is this is called your static memory. Okay, this is static memory. Again, yesterday we talked about the difference between static and dynamic, and this is dynamic. Okay, so static means that before the method actually initializes, the memory would be taken and assigned to the method or all the underlying variables. For dynamic memory, it's available on the go, so you have to request it. So a program or a method which is using static, would that be faster or the one which is non-static, or in other words, dynamic?
Static.
Static would be faster. Why?
Dynamic would be faster.
I think it depends on the program and what it functions.
Dynamic uses less space. You said static would be implemented first or something, and that would slow the system down somehow.
Okay, static means that take memory now.
Yeah, that
take
part.
memory now. And naturally, if the memory is already there, this should be faster. Okay,
Yep.
But the trade-off is that what if you don't use this memory? So there could be wastage. Okay, you may be wasting memory. Well, what if you don't use it? you already took the memory and you decided not to use it, so the memory could be wasted. On the other hand, for dynamic, okay, for dynamic, take memory as required. Okay, we don't go and ask to get all the memory. All right, so this is going to be slower naturally. Okay, it's going to be slower. But on the other hand, okay, the plus point is that, okay, this is minus. So the plus point over here is we're more efficient. Okay, we're not wasting any memory. So there's always going to be two approaches. So static, if you want your program to work faster, you're going to go and take the memory now and yeah, use it. But on the other hand, it could be a wastage. But one thing which is very important is the relationship between the CPU and the memory. You know that CPU is very fast. Can somebody tell me usually what's the speed of a CPU?
The speed of a CPU?
Yeah.
Gigahertz?
Yeah, it depends. Like 3 gigahertz. Depends.
How do you measure the speed of your CPU? Let's say you have this processor. You have Intel, I don't know, i7, okay, with 3.0 gigahertz. What does that mean? Okay, what does this tell you? Anyone?
Tells you the amount of processing power in one.
I can't hear you very well.
The amount of like functions, or like the amount of things a CPU can do in a certain time.
Okay, let's say does somebody has a Samsung phone?
Yes.
Yes, me.
Okay, if you have a Samsung, what kind of Samsung you have?
Note 8.
It's Note 8. Do you know what's a processor inside it?
It's either a quad core, like what's it called, Snapdragon, I think, or is it an Exynos?
Yeah, Snapdragon.
Okay, so it's either Exynos or it's Snapdragon. Okay, so these are chipsets for mobile phones. Both of them would most likely, for Note 8, most likely is going to be an octa-core. Okay, octa-core means that there is 8 cores in there. Intel i7, okay, usually has 4 cores in there. It's a quad-core processor. But it can be different. There's different models. You can also have 6 cores and also 8 cores. But usually it's 4 cores. So the one in Note 8, most likely it's going to be 2 point something. Let's say 2.1 gigahertz. Okay, that's the frequency of your processor. And this one is 3.0 gigahertz. Okay, so of course you can simply compare the numbers. You can say 3.0 would be faster than 2.1. Okay.
But sometimes it's really weird because when you go like in a store, like you find like an i5 that is faster than an i7, let's say for laptops. But the i7, even though with a lower clock, it performs better.
True. So yeah, if you're talking about performance, there's many other parameters. So I don't want to get into performance right now because I'm just trying to explain the difference between the core speed. So this is what we call as the clock speed for one of the cores in this processor. So for this one, for instance, every core is going to run at this speed. Okay. Here, okay, most of the time octa-core processors, not all the cores work with the same speed. There's a difference. Okay. So again, if you're talking about performance, there's many other parameters. We're talking about threading. We're talking about the performance of the core, energy consumption. So like I said, there's many different parameters, but I don't want to go in there. Right now, I'm simply talking about the speed of the processor. So let's go with this one. This is really simple. So let's say this is 3.0 gigahertz, which means 3.0 billion hertz. Hertz refers to a cycle, okay? So I'm sure you have already studied this in CS175. We have a cycle, which is fetch. Does somebody remember that?
Yes.
Fetch, then decode, then you don't remember this?
Well, kind of.
Sorry?
Fetch, decode.
Run or process, store. Okay? Yeah, I don't think I have a very good writing, but anyways, a cycle is always 4 steps. Okay? Fetch, decode, execute, or run, and store the information, or store the instruction. So this means that one instruction, okay, has 4 steps. Now, different processors have different capabilities. Nowadays, most of the modern processors, they can split one cycle into 2. And they can do this in parallel, run 2 cycles at the same time. Anyways, again, without going into efficiency, what I'm trying to say is, generally speaking, as a rule of thumb, okay, we can assume that a CPU, okay, or a processor can execute 1 billion instructions. Okay, so it's just a rough estimate. It can run 1 billion instructions per second. Memory, on the other hand, is slower. So we have different kinds of memories. We have the kind of memory which is called register. A register is part of the CPU. It's usually very fast, but the size of a register is usually very small. We're talking about only a few kilobytes. Then we have something called cache memory. Cache memory is usually, again, part of the processor. It can also be available on the motherboard. Cache memory is a bit larger, talking about a few megabytes. So let's say 8 megabytes. All right. In a desktop PC, it could be 1 or 2 megabytes. On a server, it could be more. And then you have the RAM. Okay, RAMs could be large. We're talking about gigabytes. Yeah, typically a PC has 8 gigabytes of RAM. And then we have larger storage. For example, hard drive. Hard drives could be in terabytes. Okay. Now, as the size grows, the speed slows down. Okay, so speed slows down, which means that we're going from a very small memory, okay, a few kilobytes, which is really fast, almost as fast as the speed of the processor, okay, and then as we go down, as the size of the memories increase, the speed becomes really, really slow. So again, this is just a general rule of thumb. The RAM speed is almost 1,000 times slower. Okay, 1,000 times slower than the CPU. So keeping this in mind, the difference of 1,000 times, 1,000 is a very big number. So 1,000 times slower. RAM is typically 1,000 times slower than the readily available memory with the processor, which could be register. Now, why did we study all of this? Because coming back to here, static memory. Once you declare a memory location like this, okay, which is available in a locally in a local register, okay, worst case scenario could be in a cache memory. This memory, or accessing or fetching information or storing some information in this memory, could be 1,000 times faster than this one, which would be dynamically available, only available on request from the RAM. So that's the reason this is slower, and that's the reason this is faster. So this means that when you're writing a program as a programmer, or as a software designer, we have to be very considerate about these things. But any questions so far? Is this clear?
Mm-hmm.
Yes.
That's very clear.
Okay, so, all right, great. So if you don't have any further questions, let's move on. So as a trade-off, I'm going to think about a few applications and you tell me which is a better solution. All right. I would like to store the names of all the students in the university. What should I use?
As in like either static or dynamic, or
Yeah, as in static or dynamic memory.
Dynamic.
dynamic. Mhm.
Dynamic? Why dynamic?
Because easier to search. If you want to search, it's easier to find it.
Less space.
Okay, so yeah, with dynamic memory, we're talking about efficiency. Right, what if the data is changing? Let's say this year we have 5,000 students. Next year, 500 more students come in. Okay, the year after it will be 600 more students. The year after, 1,000 more students. So
Oh yeah, that would be dynamic too.
if I make an array, wouldn't that be a problem?
It is a problem.
That's why we use like linked list or array list or whatever.
Yes, good point. So that's the issue. Now we're talking about fixed sized, okay, and dynamic sized. Wait, fixed size memories are usually objects, okay, or primitive data types. These are really fast, okay, but the problem is they're fixed. You cannot change the size. Dynamic size memories, they give you more flexibility, okay. Problem, they're slow, but they're more efficient. Okay, now imagine my problem is I need to store the names of all students in PSU. Okay, so as an engineer, okay, we have to think for the future. Let's go for the next 10 years. Okay, next 10 years, right now there's 5,000 students. We can estimate in the next 10 years there will be another 5,000 students. We're talking about 10,000 students. This means if I make an array, okay, if I make an array of size, let's say 10,000, would that work? Would this be a good solution?
No.
It would be temporary, but not a good like solution.
Yeah, it is a solution, but maybe it's not a very good solution. But if I make an array of size 10,000, right now there's 5,000 students. I'm not using half of it. Half is wasted. Okay, so we're wasting our resources. But what if instead of 5,000 students, 6,000 students join in the next 5 years? Yeah, now we have 11,000 students. Could we store them over here because the size is 10,000?
No.
Yeah, so that's another problem. Okay, so we have, we have something called excess or wastage. So either you're half utilizing or less utilizing your resources, or you're overutilizing. In case of overutilizing, which means that you have to restructure your data structure. Okay, so arrays is not always a very good solution. Here's another issue with an array. Okay, or simply static memories. So imagine your array kind of looks like this. Usually your arrays have indexes. Okay, that's kind of what your memory looks like. Imagine I'm storing some information over here. Let's say I've stored A, C, D, F, G, okay, and so on. Now, let's say I would like to insert something. I would like to insert something. Let's insert B. Okay, where should it go? Assuming that everything in the array is already sorted. Where should B go? This should be the place for B.
Index 1.
Yeah, which means that to put B over here, I don't want to override C. If I override C, C is gone. So before inserting this, what I need to do is I need to shift. Okay, G goes to the next position, F goes to this position, D goes to this position, C goes over here, and then I can put B over here. Okay, so we have a problem with shifting. Shifting is costly. Why is it costly? Okay, two things. Again, every time we're looking at cost, we're always going to look at the time and space or memory.
Yes.
Okay, so shifting is not going to require you to take any extra memory. So this is fine. We can still work with the same array. Time is going to be a problem because now you have to move everything. So imagine, let's say it takes 1 millisecond to shift one item. Imagine the size of my array is 1 million. Okay, 1 million elements. And I have to shift 1,000 elements. And one shift takes 1 millisecond. So there's going to be how much time?
1 million milliseconds.
Okay, 1 million milliseconds to shift every single thing in there. 1 million milliseconds is 1,000 seconds. Do you really want your customer to wait so much? Okay, so time is a very important factor. All right, let's look at another situation. Let's say this is my array. I would like to remove C. Okay, I want to get rid of C. So what do we have to do? If I remove C, I cannot leave this empty. So in this case, we have to shift everything back. We'll shift D over here, F over here, G over here, and so on. So again, same issue. Space is not a problem. Problem is with the time. It's very expensive to shift things. Okay? So far we've established two things. Number one is on the previous slide, we saw that fixed size is a problem. Okay, and the second problem is shifting. So these two major problems make our arrays look bad. Even though arrays are static memories, okay, you declare them once in the beginning of the method or whenever you want to use them. The memory is readily available to you and you can use it as you want. So arrays are faster, but they have these two huge problems, which is shifting. Every time you want to insert something somewhere in the middle of the array and you want to remove something somewhere from the middle of the array, you have to shift. And shifting causes your program to become slow. The other issue was a fixed size, which is once you've reached the total size, okay, you have to extend it. Like, if you want to extend the array, what do we have to do? What's the solution? Let's say here's my array. Okay, very small.
Create another array, but then
A, B, C, D. Let's say the array is full. I would like to insert something else in there. What should I do?
create a new array.
Yeah, I cannot tell my customer, hey, I don't have any more in memory available.
Mm.
We have to come up with a solution. So one of the solution is we double the size of this array. We create a new array of size 8. Okay. And we're going to copy everything from here to here. So A goes here, B goes here, C goes here, D goes here. And this would be empty. And now we can go and store E over here.
Yes.
Okay. But what is the cost of this? Is that a problem?
It takes time.
Remember two things, time and space or memory. Did we use more memory?
Yes.
Yes. How much more?
Double.
Double. Okay, that's not really good. You cannot tell the customer, hey, now the cost of your program is going to double. All right. What about time? Did we take more time?
Yes.
Remember here, we just say that shifting takes time and shifting is bad. Aren't we kind of shifting everything from the old array to the new array?
Yeah.
Yes.
Yeah. So here we're copying the contents of this array into the new array. Okay. So good or bad?
Good or bad? Good question. I think it has its own applications. Like it's good in some cases, but it's like not good at all the time.
Okay, I cannot pass this as a silver bullet solution. Okay, that's not the one solution. It has its merits. Okay, if you know that your data is not going to change a lot, I would like to store it in an array because arrays are fast.
This is the array list process, right?
Yeah, I'm coming to
Java.
yes, and if your data is changing a lot, then I would not be willing to use an array because array would be a problem for everybody. Now, this is exactly how Java implements. I'm sure all of you have already used the array list in Java. This is part of the collections framework. Okay?
Yeah.
So in an array list, whenever you want to add something, if the underlying array is full, this is what the array list does. It goes, it creates another array of double the size, and it copies everything from the old array to the new array. So is this a good data structure or a bad data structure?
It's good but slow.
It's bad because it's slow, okay? It's not very efficient, and that's a problem with Java. Okay? C++ does not have this. You do not have this. You implement your own linked list. Java allows you to use this. Okay, it's a makeshift. For a programmer, it's easier to use, but it's not efficient at all. Okay, so today you've learned the first thing. Hey, in CS101 and 102, the only thing you learned was, hey, Java is the end of the world. That's your solution. But the first day of CS210, I'm telling you, Java is not a perfect programming language. There are many problems there. Okay, so keep this in mind. This is the first one. And as you progress, you're going to learn about more mistakes later on. Okay, any questions so far? Is this clear? So now we're going to learn the basics of linked objects. Okay, we saw that arrays are perhaps not a very good solution, especially if you do not know the size of your data, or if your data is changing very frequently, which is the case for most of the applications in the world. Okay. The second thing was Java's implementation of array lists is also not very efficient. It's slow. For a programmer, it's easier to use, but it's not very efficient. If you're writing an efficient program, it's not going to work. So we have to come up with a better solution. Okay, so let's learn linked objects. What is linked objects? We already know about if I create a class like this, if I say something like public class, let's call this node. Okay, and here I'm going to define an integer value. Let's call this thing x. Okay, and I'm going to define a node method. What do you call this method? Is there a name for this method?
This method.
The method which has the
This
same
is
name as
constructor.
the name of the
Oh
class.
yeah,
Constructor.
Recursion.
recursion. Yes.
What are you talking about? This is
Oh,
construct.
it's the constructor. Yes, yes.
Yeah. So
I mean, your curly
wait,
brackets
tell me
don't
the
look that
class.
beautiful.
Okay, let me put it this way then. All right. So this is my very simple class. It has only one constructor, and which is initializing x equals 0, which is a member of the class. Well, what do you call this? Member, field, attribute?
Hmm.
I don't know.
Default.
Variable.
Default, is it?
What did you study in CS 102?
Um,
What do you call it?
attribute. I don't know. We didn't actually call it anything. It was just like a variable.
No.
Oh yeah, field. Like okay.
Member of a class. Okay. So there's multiple names for it. It depends on what you want to call it. All right. So let's say I have another class, some other class, and some other method. And inside this method, I'm writing some code. If I say this, node n equals new node, okay? So what happens is in my memory space, in my program space, is going to create n, okay? N, and is going to assign it some new memory. Like, what does the
Yes.
node look like? What is the storage space? This
It
is
has
all,
x.
there's only one variable. Why not? You can store x over here. By default, of course, it's going to be 0 because of the constructor. If I want to change this value, what do I have to say? I have to say n dot x
Value.
equals to 1. Okay, so this will go and change this to 1.
Yes.
Okay, let's create another one. I want to create node n2 equals new node. Okay, and here I'm going to say n dot x equals to 2. So again, if I want to illustrate or draw this, I'm going to have n2. Okay, and we're going to go and put 2 in there. Again, by default, it will be 0. But when you say n dot x equals 2, you simply go and put 2 over here.
Or just write it in the bracket, like new node too.
So far, so good. Yeah. If you want to write in the bracket, you have to define another constructor. You would have to do something like this. You have to say node integer x. Okay, you're going to say this dot x equals to x.
Yep.
Yeah, for that to work. Yeah. So if you want to do this, okay, you would do something like this. Node n3 equals new node, and we're going to pass it the variable 3. Okay, so again, this is just a revision of CS102 that we studied before. Now, what I want to do is, for me, handling 3 different nodes is not a very good idea. Okay, what we can do is we can create an array of this. Like, we're going to consider the same code. Okay, should I rewrite it? I really don't want to rewrite it. So let me do it this way. Okay, simply reusing the same code. Okay, now think about this. Okay, you're going to help me with this.
Okay.
This is an array of type node. I would like to go and put these values over here. Like, what should I do?
Then you do like N like with the array looking brackets. I know. I can write it down.
Node n equals new,
And then node bracket. And then 3 is the size.
like this.
Yeah, the brackets. Yeah, exactly. Basically.
Okay.
And then a node at 0 or n at 0, yeah, equals 1.
Okay. Can I see that?
Not really. You have to say like n dot x equal 1 or something.
You have to do like this: n of 0, x
Dot x equal 1. Yes.
n of 1 dot x equals 2.
And then n dot
2 dot x equals to 3.
yes.
Okay. So this code is going to implement this array of type nodes. But again, we have the same problem. We cannot really go with the arrays. Like, what if I want to insert another one over here? And I would like to put x equals 4.
So we have to do a link object.
Can I do something about this? Can I change the size of the array once it is declared?
Yeah, create a new array and then blah blah blah, just like the.
Yeah. So what we saw before, again, that's not a very optimal solution. So we'd have to destroy all of this, create a new one with size 4, and then copy everything from the old one. So again, it's not a good solution. So what we're going to do is we're going to modify our code. Okay. So I will just modify this code again. Okay. What I'm going to do is here, I'm going to define node next. Okay, so now we have two attributes. This is one attribute and this is the other attribute. I'm going to change this code. I'm going to say next. Okay, now remember, next is data type is node.
Which is a recursive.
No, there's no recursion.
Oh, okay.
It's just an object. Okay, it's an object data type, which means that I can store null. Okay, in the object data type.
Okay.
Okay, so far so good. Now, what happens if I create this? If I say node
n equals
new node. If I say that, okay, what's happening is in the operating system,
you have two objects that you need.
An object. Now my object contains two things.
An integer and
this one is integer x, and this one is node next. Okay, so there's two parts to my object. There's two attributes over here. Now, if I would like to put one over here, let's say I want to store one over here, I will say n dot next equals to, sorry.
Yeah, n dot x.
N dot x equals to 1. And I can say n dot next equals to null. Okay? We usually use this symbol to, this is the ground symbol. I think engineering students study that. So it means null. Sometimes we also use this symbol of phi, null. So it's okay, you use this one or that one, that's fine. Okay, now let's say I want to create another one. I want to have n2. And I want to copy 3 over here, and I want this to be null. What code do I have to write? Anyone?
You want to create okay, so create node n2 equal new node.
Same steps as the previous one, but with 3 as for x.
Yeah.
Right. So we're going to say n dot x equals to 3, and n dot next equals to null.
Do we need to write n dot next equal to null, or is it already null? So we don't need to.
Right now, you don't have to, because it's already here in your constructor.
Yeah.
So
Okay.
whenever you say that, by default, it will become null because you're defining this in the constructor.
Mm-hmm. Okay.
Okay. Now I'm going to show you something interesting. We can connect these together. Okay. How? So
Yeah, linking.
I can do this. Okay. How? All I have to do is just write one line of code. I'm going to say
And
n
dot next
dot
equals
next
n.
equals to n2.
N2.
Okay. So what does
Wait.
that mean?
Oh yeah. Sorry.
It's not null anymore. It's pointing to this object.
N2. Mm-hmm.
Okay. So usually when I'm explaining this, I give the example of the car and the key. So imagine this is your car. This memory location is a car, and you can access it using a reference, okay, n, or simply a key. So a key
Mm-hmm.
opens the car. Like, is it possible that I can have two keys for this car? Is it possible to have two keys for a car?
No.
Yes. Yes.
Yes.
Maybe. Yeah.
Think in regular terms. I mean, you have a car, you have two keys.
Oh, okay.
Yeah. So you have one key, and let's say you give the other key to your brother.
Mm-hmm.
So think of it like this. This is your car. This is your brother's car. This is
Okay.
your car, your key, your car. This is your brother's key, your brother's car.
Okay.
Like your brother had two keys for the car. He gave you one key, and you kept this key inside your car. Okay?
Yes.
So let's say you want to access, you want to change this, I want to change this thing to 5 using your key. How can I do it?
You can like n dot next dot next.
I will say n.
N dot next dot x equal 5.
Yes.
Very good. So n dot next is the key for your brother's car. And I'll simply say dot x equals 5. So I'll go and change this value. Okay? So we were able to link two objects together to create a chain. Now this is dynamic. You can grow this, you can shrink this, and has a lot of benefit when it comes to data structures or performance and efficient code writing.
Mm-hmm.
Is this clear?
Yes.
Okay. This information
Yes.
is available in the video. If you already watched
Doctor, I have a question.
sure.
Do we have always to fill next with null?
It's always a very good idea. Why? Because later on this week, inshallah, when we start talking about linked lists, we use the null as a sentinel value. If the null is not there, you can confuse the program. So we will see this thing later. Why is it important to have a null in every single node?
Okay.
So far, so good. Any questions?
Not really.
Okay, great.
All good.
All right. So using the same code, I'm going to copy this. So here's the code that we wrote. And I want to do something. You're going to help me write code for it. Okay, I want to do this. What should I do? What code should I write?
We should create like a node and equal new then fill it similar to the what we did before.
Okay, let's go like this. Let's create a key P, and
Doctor, we create 3 individual nodes, right?
exactly.
Yeah. Then we make the first one refer to the second one, the second one refer to the third one by using the dot next.
Very good. So yeah, go ahead. What should I do now? What should I write?
We identify, so node n equals the first one, which is 1, new node.
Okay, I'm using the constructor.
Yeah. Then node p equals new node 2. Node s equals new node 3. Then n equals
okay. How do you make the link?
So n dot next.
N dot next is equal to p.
Good.
And then
p dot next.
first we have to connect as well p to s, correct? Or can we
p dot next equal s.
Yeah, you already did this thing. Now do this one.
Yeah, so p dot next equal s.
Okay, so that's it.
Now, yeah.
How about this? Should I say s dot next equals null or no need?
You should.
I mean, it's in the constructor, so
it's already there. By the way, you're using this constructor. This constructor is not initializing it.
Oh, okay.
I should say next equals to null. Okay, so now you don't have to worry about it. If it's already there, you don't have to worry about it. There you go. Right. So you're getting the hang of it. This is easy. All right. What if somebody wants you to do this? Okay, I'm going to draw really fast. Okay. Here you go. What should I do?
For loop.
You can use a for loop.
Yeah.
Okay, we're going to use a for loop. Yeah, we don't want to have 100 variables for every single word. Okay, so what should we do?
So first of all, we do the n, the first one. So node n equals whatever, or like 1. And then we do a for loop with the size of whatever we want. For example, from 2 to 1000, or like 1001.
I can do this. I can say n dot next equals new node 2. Get it? So this is n dot next is this node, n dot next equals to new node, and we can go and create a new one over here. And then I can say n dot next equals to new node 3. And then n dot next equals to new node 4.
But this way we will have so many lines of code just to reach 100.
Yeah, this way we're not using any variables. Okay, here we were using 3 nodes, 3 variables. Here we're just using one single variable to create all these nodes. But now
but for a for loop to work, we should have at least 2 variables.
Yeah, now this is for a programmer, it's becoming very difficult. We have to type and type and type. So it's better to use a loop. Okay, what we can do is we can use a temporary variable. Okay, what we can do is we can create the node and move forward. Okay, so we're gonna say node temp equals new node. Okay, store the value, whatever value you want to put in there, and we're going to say n.next equals to temp. Okay, so n.next equals to temp. It's going to connect it like this, and then you go backwards. Okay, loop it again. So this will become
equal.
Okay, go ahead. copy the value in there. Okay, and then you simply say n.next equals to temp. But wouldn't that create this? Yes, no?
Wouldn't what create what? I wouldn't the temp create 3?
If I loop it again,
Mm.
n is still here. So
Yeah.
my code is saying n.next equals to temp. Temp moved over here. So n.next right now is this one.
Yes.
But if I rerun the code, that's going to connect this with this one. Okay, if I loop it again, temp will go to the next node. Let's say there's 4 over here. And then we say n.next equals to temp. So n.next becomes equals to this one, temp. So we're kind of forgetting this. These are not connected anymore.
Yeah, okay.
Okay, so you have to be very careful about this. Working with loop is not easy. You have to completely understand how this is working before you can go and use it.
Yeah, okay.
So a good idea is to have something called an anchor. You know what's an anchor?
The ship thing where like it shouldn't move, like whenever it wants to park or something.
Kind of looks like this.
Mm-hmm.
Yeah, so it's like a brake, hand brake. So what we can do is we can park the anchor on the first
head.
So before the loop moves, I'll simply say head, of course it's a node, equals to n. So it doesn't move. And now inside the loop, I'm going to add another line. I'm going to say n equals n dot next. Okay, so let's go over this again. So we're starting from here. Okay, let me wipe this off.
Doctor, isn't it head equals n dot next?
No. So we're starting from here. Node head equals n. So it's already pointing to here. Now you say node temp equals new node. So here's my temp. Go and put 2 inside it. And then we say n.next equals to temp. So this is n right now. n.next equals to temp. So we point over here. Okay. And then we say n equals n.next. So n is going to move. Okay. So it's not n anymore. And we say n equals n.next. So n.next is this one. So n will come here. Okay. And then go back to the loop. Remember, the loop is starting from here. So we say node temp equals new node. All right, so this becomes a new temp. We go and copy 3 in there. And then we say...
Doctor, we don't need to say node temp equals new node. Can't we just say temp equals to this number? Because I think in the code, if we re-identify it, it's a problem, correct?
Yes, this could be simplified. Okay, I can simply say n.next equals new node. But this is towards optimization. So we'll talk about these things later. Okay, so right now just keep it simple. All right, so now this is the temp. So I'll say n.next equals temp. So this is n right now. n.next is this one. So we connect this. Okay, and then n equals n.next. So this is going to move over here. This becomes n. Okay, so again, you keep repeating this thing. If you repeat it 100 times, eventually you'll get over here. So this would be the temp, and n would be the node 1 before it. It should be head.
So doctor, the head would still be the head, or like will it change?
Exactly, head did not change. So the beginning. Okay, so it's important to remember this, because if you keep moving the temp and keep moving n, you cannot go back, because all of your pointers are in one direction. They're going from 1 to 2 to 3 to 4. You cannot really go back. It's one directional.
Yes.
So what we've studied today is the basis for a data structure, which is called singly linked list. Okay, single. Okay, So we're going to talk about singly linked lists. So again, sometimes it's called single or singly. Okay, so the idea is a singly linked list has a head pointer and we have objects that are connected together using chains. Okay, there you go. Very simply, this is a single linked list. But didn't we just study this a few minutes ago?
Yes.
Yes.
Yes. So you already know the basis for this data structure. Okay. What's the difference now? Previously, what we saw was the inner working of a singly linked list data structure. But now we're actually going to go and define the API for a singly linked list. So this is the API. Like yesterday, I told you what is an API. Can somebody tell me what's API, just for the sake of revision?
Application prioritization interface or something.
Application
programming
interface. Okay, so briefly, what is it? So we forgot?
It's like NetBeans, right?
No.
The features of like the application that we're using, like for example, NetBeans or something.
Is it like I'm not sure how to explain it, but it's like a part of a code where you can grab from a third party.
Okay,
like
good.
wrapper?
Yes. So API is a definition. It's a class definition without the code. So when you want to sell, the application, when you want to sell your code to somebody, you're not going to give the code to other people. You don't sell the code. Okay? You go and buy a car. You go to Toyota or Mercedes or whatever. You go to the showroom. You pay the money and you buy the car. Do they actually tell you? Are they selling the code to you? Are they selling all the things inside? Are they giving all the definitions and design diagrams?
No, just like the usage.
No.
Like the
They don't
methods.
give you a user manual. That is, if you need it, they can simply go and drive the car.
Yeah.
Okay? So that's the application program interface. So as software engineers, when you want to sell your product, of course your product is software, so you don't want the customer to go and play with the code. Okay, two reasons. Number one, you don't want them to hack.
Security.
Okay, security, because they can simply go and make changes and resell it as their own program. That's a problem. The other thing is, obviously, you don't want them to play with the software. Okay, they can damage different things. And in US, it's very common to get sued because of this. So we do not give the code. What we give them is, okay, this is how you can use the software. So class single linked list, the things it can do. We want it to be able to insert something. Okay, remember the three things I told you? Insert, remove, search.
Find, yeah, search.
Okay, so these are the three things we want the user to be able to do. We don't want him to know anything else. How the code is implemented, everything is going to be hidden. They only know how to insert something, remove something.
But doctor, isn't it API like a more general term? Like you find the documentation online for like the code of each thing.
No, of course.
Especially
don't think singly linked list. Think of a program that you're selling to somebody. Let's say Hunger Station comes to you and they ask you, could you build the software for us? Okay, let's say Microsoft comes to you and they ask you to build the software for them. So you build the software, you don't share the code with them.
Okay? Yeah, okay.
Yeah, so it's just like your mobile phone. You want to download an app on your mobile phone. Are you also downloading the code? Can you actually look at the code?
I mean, you can decrypt and like try with some tools.
No, that's reverse engineering. That's something else.
Yeah.
Yeah. It's the same thing. That's something else.
Doctor,
Yeah.
do APIs always need a server to run?
No, API. It's again, it's not. It's a specification. It's just an explanation. Let's say you want to hire somebody to write program for you. Okay, you're going to tell them this is what I need. You don't care about how they're going to implement it. You're only concerned with how the application, how the software is going to work.
Oh, okay.
So these are some of the things that I want my data structure to do. I want to be able to insert something, remove something, search something in my data structure. Okay, apart from this, we can add a few more things. You can add whatever you like, but a very common thing would be to check if it is empty. You can say is empty. Okay, if it is empty or not. We can also check the size. What is the current size of my list? Okay, so let's go with these 5. These are the 5 most common things you do with the data structure. So let's go with these 5. All right. If I want to insert something, I have to provide information. What is it that needs to be inserted? So what do you want to insert in a linked list?
First, you need to define the type that you want to insert.
Good. You need to define what needs to be inserted. So is my linked list storing integers, doubles, strings, or is it storing more information, like let's say information for a student? What kind of information would be needed for a student?
It depends on the object.
So we were talking about student IDs, phone number, his name, okay, blood group, whatever. You can throw in whatever you want. So every node is going to be storing all of this information. But let's keep things very simple. Okay, we're just learning the basics. Of course, you can extend it to whatever you like. So let's say I want to be able to insert an integer. Okay, I'm assuming that every node over here simply inserts an integer and that's it. But when you want to go and insert something in the list, okay, should you simply go and insert it, or should it give you some kind of warning, some kind of error message, or confirmation that I have inserted it successfully or it was not successful? Should we do that, or there's no need for it?
If it's a user, like, I don't know, outside user, then you need a confirmation. But like if you're programming the thing, I think you don't need to.
Yeah, so basically what I'm trying to ask you is, should it return void, or should I return something else? So again, as a software engineer, as a designer of the program, okay, we have to consider all these options. Okay, when we say void, this means well, whatever happens, if it was able to insert something or not able to insert something, we're not going to return anything. We don't care about that. But if your customer is very cautious about this, okay, then of course you would like to return something or throw an exception if there was an error or something of this sort. Okay, if I want to remove something.
Yeah.
Remove means that I have to first go and search something.
Yes.
Yeah.
Then
say, something was stored over here. I like to go and remove it. This means I need to first look for it, and then I need to remove it.
Take the references from it, like take the arrows from it.
Yeah. So usually you should be able to remove it. Okay. So normally what we do is we remove the node and return this node back to whoever called this method, whatever they want to do with this removed node.
Okay.
Search. Okay. Let's say I'm searching for some information. So we start from one place, we go and look until you found something. If you find something, we're going to return a reference to this. Okay? So for example, let's say this particular linked list stores information about all the students in the university. Every node in there contains information about every single student, like which courses have been completed, which courses are left, how many courses were registered, okay, if the tuition fee was paid or not. So all this information. Like, how do I search this information? Should I search by the ID number?
Yeah, something different, like in each list or like in each object type.
Okay, normally you're required to have a unique value. So every student has a unique ID number. Okay, it's not possible that one number or two students have the same number. That's not possible. That's why you have a unique number. So I can go and search for information. Whenever I find a node which contains this ID number, what I'm going to do is I'm going to return the entire node to whoever is asking for this information. Okay, so we simply return a node. All right, it's empty. Okay, how do I check the list is empty?
Boolean.
So it's either empty or not empty, so it can be Boolean. Okay, I don't need to pass it any parameters. Same goes with the size. Okay, no need to pass any parameters. Size could be integer, could be long, could be double, I don't know. But I think integer is big enough. Integer can store a few billion values. So
I mean, we define it anyways in the code, so like you put the anchor thing.
Yeah, we'll see this thing how this is going to work.
Okay.
So there you go. This is the API. Okay, we call this thing API. All right. Do we need to define a constructor?
No, because it already has the code, and then you're just using the product.
Okay, we need to define a few things. What else? So these are the methods that the user would be able to call, but for internal workings, okay, most likely these things would be privately defined. You know private, yeah? The difference between public and private. So we would like to define integer size. Okay, this is different from this. This is a method, and this is just a variable. But we need to remember the head. If you don't have the head, you won't be able to find where to start from. So we have node and a head.
Okay.
Okay. So these two are necessary. Like we can define both of them as private. So the person who's playing with this data structure won't be able to see this. They would be able to access only these methods. So far, so good?
So far, so good.
Okay. Did you guys study UML?
I think yes. The Unicode thing.
What's UML?
UML is Unified Modeling Language.
No, I don't think
so. Like it was mentioned. It wasn't like deeply.
No.
Okay. Did you guys take one or two with Dr. Al-Hawari or Dr. Anis?
With Al-Hawari.
I took it with Dr. Anis.
Okay, I remember Dr. Anis used to cover this. Anyways, this will be covered in another course which is called SE201. Most likely we'll take it next semester. But anyways, in one or two, we do mention this very briefly. So UML, it's a language that allows you to illustrate or define your classes. So if this is my class, I can write it like this. I can say the name of my class is SLL. Okay, I'm going to define integer size. I'm going to define node head. Okay. So this is the name of the class. And these are the attributes, and these are the methods. So here I'm going to put insert, search, and so on. Okay. So this is one class. Imagine your program has multiple classes, so you can put them together all of these boxes, and then you can have a relationship between those classes. Anyways, don't worry about it. If it was not covered, that's fine. Okay, so let's see how this is going to work out. We're going to look at things one by one. Okay, remember in this API, did you see node somewhere?
Do you see node? What do you mean again?
Yeah, do you see node somewhere? Have I mentioned node somewhere?
In head.
There's node. Somewhere else?
And remove, search.
Okay, everywhere. But did you define the node class here?
Nope.
Nope. Okay, this means we also need to define the API for the node class. Okay, let's see. Did you guys study embedded classes? Can I put a class inside another class? Or not?
No, I don't think so.
You're not. Okay, that's fine. So in NetBeans, when I'm programming, I can put multiple classes in the same project. Do you agree?
I mean, yeah, we agree.
I
saw it on YouTube, but like we didn't do it in the course.
Oh, in CS101 you did not program at all.
I mean, we did program, but like we didn't have like multiple classes in one in one thing, in one page.
I see. Okay. Right. Well, in this particular course, the projects that I give, it requires students to have multiple classes together. Anyways, well, I'm not planning to do a project in this particular summer offering, but in a regular semester we do that. But let's see, if you, some of you want to practice, I can give you a sample project to work with. Okay. So continuing with single linked list, going back. So this is what we're trying to work with. So far, we've said that your API is going to contain these methods. So we're talking about 5 different methods. We have insert, remove, search, is empty, and size. Right. What's the node class? We already talked about it. We're going to continue working with the same class that we saw before. Okay, talking about this one. So we're going to have these 2 classes. We're going to work with these 2 classes at all the times. Okay. So let's look at the single linked list. Okay, we're going to start with insert. In my API, insert method takes a parameter and returns something. What is it returning?
Void.
Yeah, it returns void, and it takes integer as a parameter. Okay, so remember, my list kind of looks like this. Head. In the beginning, the list would be empty. There's nothing there. Okay, so if I would like to insert something, let's say I want to insert 1. Where do I insert? Yeah. We'll go put 1 over here and make this null. Okay, so we'll check. If my list is empty, okay, if my list is empty, what I will do is I'll simply say head equals new node 1. Remember the constructor which is taking a parameter? Yes. So I'm going to say head dot next equals to null. Okay, we make this null.
Yeah. Okay.
But what if let's insert 2 in there? I want to insert 2.
Okay. Then after the empty thing, you write.
This is not going to work because my list is not empty. So this means I need to insert it somewhere. I have 2 options. I can insert in the beginning.
Else.
Insert at the end.
Yeah.
Okay. Imagine my list kind of looks like this. Let's say I want to go and insert this over here.
Yeah.
Okay, so basically, insert at the end. Okay, like to insert at the end. Okay, how can we do this?
Create a new
I can create
object.
a temp.
Node.
Okay, I can create a node temp equals to head.
Yes.
Okay, so you can create a temp, just pointing to the same memory location as the head. Okay, and I can move. So let's say there was other nodes over here. Okay, let's say there was something over here, something over here, something over here, and we'd like to go and insert it after this one. Okay, so node temp equals head. I'm going to run the loop while temp dot next is not equal to null. Okay, I will say temp equals to temp dot next. All right, so it's going to happen. So we're saying node temp equals head, temp goes here, while temp dot next. So this dot next, is it going to be null now?
No.
No, it's connected to some other node. Okay, so this one, this node that contains one dot next is not null. So if it is not null, we say temp equals temp dot next. So temp goes to this one.
Yep. And then checks if it's null.
So we go back and check again. Temp dot next is null. So now this is the temp. Temp dot next is also not null. It's already connected to something else. So basically, this loop is going to keep moving all the way until we reach here. Okay, so some node, let's say these are connected. So temp dot next is not equal to null. No, it's not. Go on. Temp equals temp dot next. So this becomes temp. Okay, so while temp dot next is null. Okay, this is the last one. This is null. There's nothing after it. So it's going to stop. Okay, where's temp now? It's sitting on the node which is at the end.
Yes, so if you want to add it, then
now if I want to add it, I'll simply go and add it. I'll simply say, hey, temp dot next equals to new node, and put in the value, this x value, whatever that is. So that's going to create this dot next is equal to new node, whatever the x value is. Just go and put this over here. Okay, so if you've successfully inserted something, we can increment the size. Remember, there is a size variable.
Yeah.
Whenever you insert something, we have to increment the size. So simply go.
Shouldn't you do this inside the while loop?
No, size inside the while loop? Of course not.
No, not size. I mean like the temp dot next.
No, if you do this thing inside the loop, that's going to be a problem. You're adding so many nodes within that. We don't want that. We're using this loop to move the temp from the head all the way to the one at the end.
Yep. It will create new nodes in each position.
Yes.
Yep.
So far, so good?
Yeah.
Okay. Like, is this a good approach? How long is it going to take to insert something almost always at the end?
A lot of time.
Yeah, that's costly.
We could just see like the size -1 or like size, and then like we add after the size.
Okay, this is costly. So can we have another solution? Why don't we define a new variable called tail? Can I do that? Let's say I can define node tail. So every time you go insert something at the end, okay, we'll make that equal to tail. So for example, imagine if I was remembering this. Imagine if I remembered this is a tail pointer, which almost always points at the end. Okay, so I don't have to run this loop. No need for that. All I have to say is, okay, I don't need any of this. all I have to say is tail dot next equals to new node. Okay, put the value x in there. Okay, so tail dot next. This tail dot next equals.
And then sides plus plus, or like
so
add
put
the
the
sides.
here, and then simply say sides plus plus. But remember, tail must be the last value.
Yeah.
Or last node. So this is not the last node now. This is the last one.
So we have to make tail as the
tail equals to tail dot next.
Yeah.
Right. So tail dot next is this one. So this becomes the tail. So now this becomes the tail.
Yeah.
Okay. So is this faster?
Yeah, it is much faster.
This is faster. What's the cost here? What did you add?
Space.
We added only one variable. Only one variable. I hope nobody's going to mind if you added only one variable.
Yeah, okay.
Compare this to, imagine the list is very long. There's 1 million nodes in this list. Okay, so every time you want to go insert something at the end, that's going to be a problem. Your program will become slower and slower and slower. But this way, your program is not slow at all. It's very fast. Okay. Why don't we consider inserting at the beginning? We don't even have to worry about the tail. Okay?
Yeah.
So look at this. What if I have to insert?
Just have to change the head
at the beginning. Okay? So all I have to do is just change the head.
Yeah.
So here's a head. Okay, imagine we already have lots of nodes.
And then you create a new head and then.
Okay, so all I'm going to do is I'm simply going to say node temp equals new node. Okay. X, of course, X is this value. So what's happening over here is we go and create a new node temp. Okay, put the X value in there. And now we're going to say, okay, let me go with this. So temp
equal
dot next equals to head. What does that mean? So temp dot next equals to head, this node. Currently this is head. So this node points over here. Okay, and now we say head equals to temp. So this will go away, and there you go. You see what happened?
Yes, yes.
Is this clear or not? Should I do it again?
It's clear, but why can't we just like make it the new head?
Okay, let me do it again.
Like, why can't we make tab a head and then like remove the old head?
Okay,
like make
point.
it.
But what if you lose it? If you lose the head, okay, you would lose the entire list.
Oh, okay.
So think like this. Okay, here's the head. Okay, so we have some node here. There's something in there. And we would like to insert a new node over here. Okay, we want to do this. And then we want to do this. Okay, so this is my temp. I'm going to say node temp equals new node. X in there. So whatever is the X value, we put this over here. Now we say temp.next equals to this one. Currently, this is head. Okay, currently this is head. Right now, this is head. But now we want this to change. We want head to point over here. So head equals to temp. Okay.
Yep.
There you go. And now we simply say size plus plus.
Okay.
So now we don't have to worry about writing all of this code. Okay, if you decide to insert in the beginning, that's what is needed. Okay, there's 4 lines of code. We always go and insert in the beginning. Is this faster?
Yeah, Doctor, can't you do head.next equal tab?
Head.next
equal tab. Like above the size plus plus.
Oh, you mean head.next equals 10? No, but this was the head right now. This would be the head.
Okay.
Okay, so head.next would be this node. If you change that, it's connected.
Yeah, okay, now I get it.
Okay, so far so good. So inserting at the beginning, of course, is much faster than inserting at the end. Okay, what if somebody says, hey, no, I want it to be inserted in the middle, somewhere in the middle. Let's say, here's my list. Okay, let's say somebody says, no, I want you to maintain the order. Okay, let's say this is some list that contains this information. And he wants you to go and insert 3 in the correct position. Okay, so where should 3 go?
In head.next.
Yeah, but we don't know exactly where is 3. It could be any different values.
Yeah, so you do a while loop and then until you find something.
Yeah, so what we need to do is we need to be able to figure out where is the correct position. What is the correct position for the new node that needs to be inserted?
Okay. I think you have to do like a small code where it checks if it's bigger than the number, like the value. If it is, then
very good point. Yeah, this is exactly what we have to do. So let's say there is some technique, some idea that tells you, all right, let's figure out that this is the node. We're going to call this thing previous. Okay, and this is the following node. Okay, let's say magically we got these. So we want 3, this new node or temp node. This needs to be inserted between the previous node and the following node. Okay, so how do I connect this? I will simply say 3 or this node, temp.next will become equal to the following node. Okay, and priv.next will be equal to the temp node. Of course, this will go away. So this way you can insert in the middle. Okay?
But how can we know the previous and the following?
Very good point. How can we find the previous and the following? So imagine, look at this particular example, how I can do that. Let's say I want to insert, okay, I want to insert 3, let's say. Okay, so what I'm going to do is I'm going to use, I'm going to define node priv equals to head. Okay, going to run a loop. So while priv dot x, remember this is the x value, yeah? So while priv dot x, okay, by the way, this is called x. So while priv dot x is less than, okay, as long as this is smaller than the temp dot x. Okay. All right. Just to avoid confusion, let's call this n. So of course, in the beginning, we need to have a temp value over here. Okay. So, all right. I'm gonna also change a few things. Let's call this. All right, so it's just a pointer. We're saying node follow equals head. Okay, so in the beginning, follow would be here, while follow dot x is less than, okay, x is the value that we're trying to insert. Don't we have to do that? Okay, so in the beginning, follow would be here, right? So if this is smaller, what we do is we move forward. So we're going to say follow equals to follow dot next. Okay, so far so good? Okay, so this is just to show you the illustration, but now I'm trying to simulate it for you. So in the beginning, follow is here. Okay, so look at the code. While follow.x, which is 1, is less than x, which is 3. Okay, that's true. So we move follow. Follow will come over here. So this becomes follow. Okay, goes away.
And then again, follow.
Okay, so follow equals follow the next. So we move on. And again, we check, hey, 2 is less than 3. Yes, it is smaller. So we move on. So this becomes follow. Okay, and this goes away. Now we check again. While follow.x, which is 5. 5 is less than 3. No, it's not. Okay, this means we can stop here. Now what I can say is, whenever the loop finishes, I already know where it's follow. Can I define priv now? Can I say node priv equals to the one before it?
Follow.next. Oh, no,
follow the next is this one.
Yeah, so...
How can I know this one?
How do we do this? Like...
Yeah, we cannot do that. Because once you've gone, you have to start all over again. That's not a very good idea.
Yes.
What we can do is we can play a little bit of a trick over here. Okay. The trick is we're going to use 2 pointers. We're going to define node priv. Okay. And whenever I say this, before I say it, okay, here I'm going to say priv equals to follow. Okay. So what happens is, again, I'm simulating it again for you. So in the beginning, okay, priv is not defined. Follow is defined. In the beginning, follow.
Yeah, so each time it's going to be equal to priv until it stops.
So go and check this is not true. So we're going to make this priv, and the next one becomes follow. So this becomes follow.
And then it becomes priv.
Okay, and this one becomes priv.
Yep.
Okay, and moving on again. So this one will become follow. Okay, and this one becomes priv. And of course, this goes away. See? So we would be able to do it like this. So now we
do priv.next.
Now what you need to do is create a new node and insert this in there. How do we do that? So node n equals new node. And we're going to put the x value in there, which is 3. Okay. I'm going to connect this one. So n.next equals 2. Can I say follow?
I mean, yeah, you can. Can you? Yeah, I think you can.
n.next equals follow.
Yeah.
It's like this. How about this one? Can I do this?
This is priv.next.
Yes.
Right? Or like it's priv and then.
Yeah. Priv.next equals to n.
N.
Okay, let's connect this over here. Okay. And of course, you're going to say size plus plus. Okay, we were able to insert a node in there, and that's it. Return and finish the method.
Mm-hmm.
So we've looked at all 3 scenarios. There's a possibility the node could be inserted in the middle, could be inserted in the beginning, could be inserted somewhere at the end. But which approach do you think is the best one, the fastest one?
The one in the beginning.
The one in the beginning is the fastest. Okay, there's least amount of code. It's not costly. Insert directly in the beginning. But if you have to insert at the end, we found a solution, which is if I define an extra variable till, I can use that to very quickly move towards the end. Okay, and now the most difficult thing is inserting somewhere in the
middle.
So the solution is we use 2 extra pointers, and we use these pointers to go and find the correct previous and the following position, and we go and insert the node in the middle.
Yeah, this is one situation in the middle, right? Because like it could be not numbers, it could be something else.
It could be something else. So most likely the situation is going to arise when you're required to sort the data or maintain some kind of sorted order. So in that case, they will like to go with this. But remember one thing, when it comes to sorting, okay, linked lists are not a very good data structure. So remember that. Later on when we study the sorting algorithms, you'll figure it out. Oh, linked list would be a horrible data structure if you want to sort data. So we have arrays, which are a better solution.